Good afternoon, everyone. What I have for you today is basically 35 slides of junk, space junk. But basically what I have is basically an introduction into some of the methods that I apply throughout my thesis. But basically going to be a very brief introduction into the methodologies and some results. But basically I won't be able to cover all of the topics in my thesis, so that'll be for you to stay tuned for the defense coming up. So currently there are 38,000 tracked objects that we know of around the Earth, according to ESA's latest space debris report. This is the tracked objects, obviously. Untracked, much smaller objects, probably millions. So Earth orbit looks a bit like this when you look at objects that are over 10 centimeters in diameter. So looking at this picture, you might think, well, it's quite surprising that it wasn't until 2009 that the very first collision between spacecraft occurred. Not only that, it's like pretty much been the only one that's occurred since then that we know of. And this essentially happened between two spacecraft. The one was operational, the other one was not operational. And it released thousands of fragments into Earth orbit, prompting people to start kind of worrying about, what could happen in the future if these fragments are now orbiting around the Earth, spreading around their orbits. They're becoming new threats to the space population. So this prompted concern over this Kessler syndrome, which essentially it just means that the risk of collision between spacecraft and space debris becomes exponential, rises exponentially with every collision up to the point of basically no return. So there are several ways of dealing with this and several aspects to take into account. One of them is actively removing the debris, which is not something I do at all. The two is actually tracking the spacecraft or the space objects that you have so that you ensure that you don't collide in the first place. And number three is having metrics and ways of computing the risk of collision between spacecraft so that you can reliably assess whether to maneuver or not. So the topics of my thesis essentially involve three different things, which may or may not be related. Number one is the computation of collision probability. Number two is kind of like a bonus thing that I started doing kind of recently, which is re-entry window prediction schemes, because it's the result of a research study. And number three is spacecraft tracking with the simultaneous characterization of process noise. But this one I'm not going to be talking about today because I just don't have time. But first of all, I'm just going to quickly define something that will be present throughout the thesis. But essentially, we assume the state is given by a position and velocity for spacecraft, which you may assume that it's given by this x here. And with every estimate, you'll have some uncertainty given by its probability distribution. If you have a good estimate, then the uncertainty will be lower. And if you have a bad estimation, then your uncertainty will be larger. You may assume this uncertainty to be represented by a Gaussian distribution, or you may approximate it with samples, say by using a crude Monte Carlo simulation of sufficient samples, if you want a proper approximation of the covariance that you have for your initial conditions. So the first topic is probability of collision. I can take roughly 20% credit for this image. But basically, it's extremely hard to model collisions. So you have a numerical scheme, you're propagating an orbit in time, and it's really hard to get the step sizes of the numerical integrator just right so that you actually compute a collision, because spacecraft are moving at relative speeds of perhaps 14 kilometers per second. So you need something, so the distance, the relative distance is wildly oscillatory. So you want something that maybe behaves a bit more smoothly so that you're able to predict these collisions and actually capture them in your numerical schemes. Another thing is that classical ways of computing this probability of collision usually assume Gaussian distributions at the time of collision, which this is something that might not always be the case, especially after long propagations in orbit. This Gaussian assumption kind of breaks down. So with crude Monte Carlo, which is a technique I mentioned earlier, you can approximate, other kinds of distributions that are not necessarily Gaussian. But these are expensive. Why? Because collisions are rare events. So in order to get just one collision, if you have, say, a large uncertainty, in order to just get one collision, you need loads of samples, maybe millions of samples. So in high fidelity, this is costly. So we propose a technique called importance sampling here, IS, which is a Monte Carlo variation, but essentially it deals with generating a distribution which generates more of these rare events so that we can more efficiently essentially compute them and be able to cheaply assess the probability of collision. But first, the metric that we propose, I'm just going to go over it in a really intuitive way. I'm not going to use loads of maths or anything. I'm just going to basically show you what the metric consists of. And it's essentially transforming the problem between having a 12-dimensional space, so like 6 dimensions for each spacecraft, assuming 2 spacecraft, and transforming them into just 2 variables, which are defined by these 2 over here. And they're basically given by, well, one of them is this gamma here, which is the radial distance between the spacecraft, between the spacecraft, and the delta is the angular distance between the spacecraft along one of the spacecraft's orbits. So intuitively, what this looks like is you map your initial conditions onto this plane here. So you have your collision threshold, which will be your hard body radius of the 2 spacecraft. So if you're in there, you're colliding. And then you map by crude Monte Carlo your distribution, your initial distribution, you map it onto the collision space at the collision time. And you see that it's kind of there at the edge. So to get a good approximation of the probability, you will have to compute loads of samples. Importance sampling generates a different distribution, which generates a higher proportion of its samples as being colliding samples. And you essentially use these samples to compute the probability of collision. So this thing here will now look like this, which you see you can plot hundreds of thousands of samples, and more of them lie in the collision zone. Now you might think, oh, well, this is a biased estimate. Like you're just generating collision events. That's not the real probability. But so in order to make them an unbiased estimate, so use them to produce an unbiased estimate, you weigh them. So these samples will not be weighed equally. And the summation of these weights will be able to be used for the computation of the probability of collision. So comparing to a high fidelity crude Monte Carlo, we see that our estimates are quite similar for a given low Earth orbit test case. But the computational cost of our method is significantly reduced compared to the Monte Carlo, which essentially means that you can attain the accuracy of the Monte Carlo high fidelity, but at a lower cost. Number 2 is the efficient prediction of reentry time windows. So essentially, when you have an estimate of when a spacecraft will decay into the Earth's atmosphere, you have some uncertainty associated to it. So you might be on the 30th of April being like, okay, well, that spacecraft is going to decay anywhere from the 3rd of May to the 10th of May, as is the case here. So that's a 7-day window in which your spacecraft could or could not re-enter. So if you get more information along the way, say you get observations throughout time, you might reduce that uncertainty and you might reduce the window because you just have better knowledge of the state of the spacecraft. So again, crude Monte Carlo, you can use it to produce histograms of the re-entry times of a cloud of samples. And again, if you use a high fidelity model, it will be quite costly computationally. So in order to reduce this cost, we employ another variant of crude Monte Carlo called multi-fidelity Monte Carlo, MFMC, which essentially uses different dynamical models. So you'll get cheap dynamical models, which exploit maybe different aspects of the modeling. And you'll get expensive high fidelity models to essentially produce unbiased estimates and just retain the accuracy. So Another thing that we use is, great. Okay, another thing we use is we assume stochastic propagation instead of just simply deterministic. This is not necessarily novel, but we do use stochastic numerical schemes to integrate these. And what we mean by this is that you have your normal dynamical model, which is all the forces that you want to compute, but you add a stochastic term given by this part here, which essentially is driven by this guy here, whose magnitude is tuned based on the error that you're committing with your dynamical model. If you are emitting a certain magnitude of accelerations, then you add this process noise term to basically account for the fact that you're truncating your dynamical model. But we just vary this coefficient just to see what the effect is on the reentry window size. We see that as you increase the magnitude of the coefficient, you also increase the window size. But you get to levels where your window size is like 10 days long, which is borderline uninformative. So it doesn't really make sense to just inflate it just for the sake of being safe. So you want to use a magnitude that accounts for the errors that you're committing in your dynamical model, but also doesn't just arbitrarily inflate the window. So this is just the last slide of results. Our MFMC, when compared to the CMC over many, many simulations, you're able to obtain a mean of the simulations and also standard deviation of your estimations, which are the shaded regions. We see that for the computation of a lower bound, upper bound, and a mean value for the reentry times, you're able to reduce the estimate variance as you increase the computational budget that you have when compared to the CMC. So you're able to achieve for a lower computational budget using the MFMC the same accuracy as a higher budget CMC. This is just what one simulation looks like. The histogram is the CMC high fidelity, and it's safely contained within a window of like just under 2 days by the MFMC, with the ground truth value of the real reentry time of this satellite that decayed in 2013. And I don't know how I'm doing with that. This is the last slide.
Finish.
Okay, now that's just all I'm saying is the uncertainty modeling, taking into account the uncertainty is crucial, especially for applications in probability of collision, because if your initial uncertainty is really large, then it just completely distorts the value of the probability that you'll obtain. So you have a large uncertainty, you're going to get a low probability of collision. For reentry, it's less crucial. All it means is that your window is just going to be larger. But you need methods to characterize this uncertainty properly. And that's where the next chapter comes in, which you have to stay tuned for the defense, which essentially estimates the sigma coefficient that we were looking at. And that's it. This is just research stuff. This guy is pending to be submitted this month, and I'm attending this conference, UCAS, this month. So if anyone else is going, hit me up. We can go together, I guess. And that's it. Thank you.